Greetings everyone, myself Muskan. I'm a student of BSc Chemistry Honors first year. Today I will discuss the topic alkyl halide. Let's start our topic. Firstly, we have the introduction of this topic. Compound obtained by the replacement of one or more hydrogen atom of a hydrocarbon by an equal number of halogen atoms are called halogen derivative of hydrocarbon. Many halogen containing organic compound occur in nature and some of these are medically useful. For example, the chlorine containing compound occur in nature. Some of these are used in antibiotic chloromycin and chlorophenicol produced by soil microorganism is very effective for the treatment of typhoid fever. Our body produces an iodine containing hormone called thyroxine, the deficiency of which cause goiter. Some synthesis halogen contain compound are very useful in health care and medicine. For example, chloroquine is used for the treatment of malaria fever, and halithane is an anesthetic agent used during surgery. Certain fully fluorinated compound is an pound are thought to be the potential blood substitute in surgery. Many synthetic organic halogen compounds are extensively used in agriculture and industry and hence are being manufacturing in large quantity every year. Organic halogen compound serve as valuable intermediate for the synthesis of variety of other classes of organic compound. Therefore, in this unit we shall discuss briefly the preparation properties and uses of simple organic halogen compound. Now we will discuss the classification of halogen compound. Halogen derivatives of hydrocarbon are broadly classified into the two types. First one is aliphatic halogen compound. These are the compound obtained by the replacement of one or more hydrogen atom of an aliphatic hydroatom by the equal number of halogen atom, depending on the nature of the aliphatic hydrocarbon, whether alkane, alkene, alkyne. Aliphatic halogen compound are the following of three types. Haloalkane. The halogen derivatives of alkenes are called haloalkane. These are classified as fluoro, chloro, bromo, iodide compound according to the type of halogen present as mono, di, tri, tetra haloalkane, according as they have 1, 2, 3, 4 halogen respectively in their molecule. For example, you can see some example: chloromethane, dichloromethane, trichloromethane, tetrachloromethane. Whenever two names are given under the formula, the one outside the bracket refer to the IUPAC name, while the given in the bracket denote the common name or trivial name. Haloalkene and alkynyl halide are the halogen derivative of alkenes. Their general formula is CnH2n-1, where X is equal to fluorine, chlorine, bromine or iodine. N is equal to 2, 3, 4. For example, chloroethane, 3-bromopropene, 1-chlorobutadiene. Haloalkyne and alkynyl halide are the halogen derivative of alkynes. Their formula is CnH2n-3x, where X is equal to chlorine, fluorine, bromine, iodine, and N is equal to 2, 3, and 4. For example, chloroethane, 3-bromopropene, 1-bromopropene. Now we will discuss aromatic halogen compound. These compound obtained by the replacement of one or more hydrogen atom of aromatic hydrocarbon by an equal number of halogen atom. These have been further classified into two major categories. First one is nuclear halogen derivative. Halogen derivative of aromatic hydrocarbons in which the halogen atom fluorine, chlorine, bromine is directly attached to an aromatic ring is known as aryl halide. Their general formula is AR in bonded with X, where AR is a short name of aryls, represent as phenyl. A substituted phenyl or other aryl group such as naphthyl, etc. Some of the example of aryl halide: chlorobenzene, 1-bromo, 4-methylbenzene, ortho-iodotoluene. Now we will discuss second type of aryl halide, that is side chain halogen derivative. Halogen derivative of aromatic hydrocarbon in which the halogen atom is linked with one of the carbon atom of the side chain carrying the aryl group are called aryl halide. Some examples are here: 1 chloro, 1 phenyl methane, 1 chloro, 1 dichloro, 1 phenyl methane, and some more examples are there. Now we will discuss alkyl halide. The monohalogen derivative of alkene are called alkyl halide and monohaloalkene, or simply haloalkene. The general formula is Rx, where R is the alkyl group and X is an halogen atom. Fluorine, chlorine, bromine or iodine are the some halogens. They also are represented as CnH2n plus 1, where X, where n is equal to 1, 2, 3, etc. These are obtained by the replacement of one hydrogen atom of an alkane with a suitable halogen atoms, which is shown in that example Rx. There is a addition of halogen atom and removal of hydrogen atom. Nomenclature of alkyl halide. In the common or travel system, the monohalogen derivatives of alkane are known as alkyl halide. Their individual name are derived by the naming of alkyl group followed by the name halogen as halide. Fluoride, chloride, bromide. The complete name of alkyl halide is always written as in the separate words. The IUPAC system, the monohalogen derivative of alkane are named as haloalkane. The individual name of are derived by prefixing the word halo to the name of the longest chain alkane. The numbering of the parent chain alkane is always done in such a way that the carbon atom carrying the halogen atom gets the lowest possible number. The IUPAC name of monohalogen derivative of alkane is always written as a word. There are some example which are shown in this tabular form. Now we will discuss the classification of alkyl halide. Classification of alkyl halide. Alkyl halide are further classified as primary, secondary, and tertiary according as the halogen atom is attached to primary, secondary, and tertiary carbon respectively. For example, iodoethane, 1-bromopropane, 1-chloro-2-methylpropane, 1-bromo-2,2-dimethylpropane. These are the example of primary halide. Now we will see example of secondary halide. 2-chloropropane, 2-bromobutane, 3,3-dimethyl-2-bromobutane. These are the example of secondary alkyl halide. 2-bromo, 2-methylpropane, 2-iodo, 2-methylbutane. These are the example of tertiary carbon. Method of formation. Alkyl halides are usually prepared in the laboratory by the following general method. Firstly, we will discuss their preparation with alcohol. The most convenient method for the preparation of haloalkane involves the substitution of the OH of an alcohol by halogen atom. This can be done by following method. First one is by the action of halogen acid. Alcohol is converted into haloalkane by the action of halogen acid. For a given alcohol, the reactivity of halogen acid in the given reaction follow the sequence HI. In most react show reactivity HBr HCl. That of alcohol for a given haloic acid follow the order tertiary, secondary, and primary. Reason: the reason is an example of the reaction is an example of a nucleophilic substitution reaction in which the nucleophile, that is halide ion, attack to the protonated alcohol molecule, which with the expulsion of water a good leaving group. Since the nucleophilicity, the tendency to donate an electron pair to the carbon atom of the halide ion decrease in the order. The order of reactivity of the halogen acid decrease in the same order. Further, since the order of stability of the carbocation follow the sequence tertiary, primary, secondary, primary, the order of reactivity of alcohol follow the same sequence tertiary alcohol, secondary alcohol, primary alcohol. Chloroalkane and alkyl chloride. Primary and secondary chloroalkane and alkyl chloride are prepared by passing hydrochloric acid gas through a suitable alcohol in the presence of anhydrous zinc chloride, that is used in a groove process. Ethanol in the presence of HCl gas and in the presence of anhydrous zinc chloride, there is a formation of ethyl chloride with water. The mechanism of anhydrous zinc chloride is helped in the cleavage of CO bond. Being a Lewis acid, it coordinates with the oxygen atom of the alcohol. As a result, CO bond weakens and ultimately break to the carbocation. These carbocation are readily react with the chloride ion to form chloroalkane. That is shown in figure. ROH plus ZnCl2. There is a transfer of lone pair to zinc. Zinc attain negative charge and oxygen attain positive charge. Then there is a formation of carbocation and zinc chloride hydroxide. When after that carbocation react with the halogen atom and it follow SN1 reaction and there is a formation of alkyl halide. If the nature of alkyl ion is such that it undergo rearrangement, the product will be rearranged alkyl halide. For example, neopentyl alcohol on heating with HCl does not give the expected neopentyl chloride but give the rearranged alkyl halide 2-chloro-2-methyl-butane, which is shown in that example. Driving force for this rearrangement is the greater stability of the tertiary carbocation over primary carbocation. If the concentration of ZnCl2 is low, the reaction is still catalyzed by acid, but no rearrangement occur during SN2 reaction. Pyridine and dimethylamine can also catalyze the reaction between alcohol and hydrochloric acid without rearrangement. Tertiary alcohol, however, react with concentrated HCl even in the presence of zinc chloride. Bromoalkane and alkyl bromide are obtained by refluxing a suitable alcohol with the constant boiling hydroboric acid 48% in the presence of little concentrated H2SO4 as catalyst. HBr can also be generated in situ during the reaction by the action of concentrated H2SO4 on KBr. Iodoform and alkyl iodide are prepared by refluxing a suitable alcohol with the constant boiling hydride hydroiodide acid 57%. HI may be generated in situ by the action of 95% phosphoric acid on Ki. By the action of phosphorus halide. Phosphorus halide react with alcohol to form haloalkane or alkyl halide in a excellent yield. Chloroalkane or alkyl chloride are prepared by the action of either phosphorus pentachloride or phosphorus trichloride on suitable alcohol. Similarly, bromoalkanes or alkyl bromide and iodoalkanes or alkyl iodide are prepared by the action of phosphorus triborate and phosphorus triiodide, respectively, on suitable alcohol. Since Pb3 and Pi3 are not very stable compounds, these are generally prepared in situ by the action of red phosphorus on bromine and chlorine, respectively. Now we will see the preparation of alkyl halide by the action of thionyl chloride. Chloroalkane and alkyl chloride are convenient prepared refluxing alcohol with thionyl chloride in the presence of pyridine. Thionyl chloride is a method preferred over hydrogen chloride or phosphorus pentachloride method for the preparation of chloroalkane. Since both the byproduct is SO2 and HCl in the reaction being gas, escape leaving behind the chloroalkane is the pure form. Now we will discuss from hydrocarbon. There is a preparation of haloalkane, alkyl halide. Haloalkane can be prepared from alkenes. Alkenes are discussed below. Firstly, from alkenes. Alkenes react with halogen to form haloalkane. The reactivity is Hi, HBr, HCl, HF. The addition of hydrogen halide to a unsymmetrical alkene take place according to Markovnikov's rule. The the rule states that during the addition of unsymmetrical reagent to unsymmetrical alkene, the negative part of the adding reagent, addendum molecules to be added, goes to that part of carbon of the double bond which has lesser number of hydrogen. However, the presence of peroxide such as benzoyl peroxide, the addition of HBr, not of HCl or Hi to unsymmetrical alkenes take place contrary to Markovnikov rule. This is known as peroxide effect or Kharash effect. From alkanes, halogens of alkanes with chlorine, bromine in the presence of light usually give a complex mixture of monodiide polyhaloalkanes. For example, chlorination of methane gives four products, that is methane, chloromethane, dichloromethane, trichloromethane, tetrachloromethane. Although substitution beyond the halogen monohalogen can largely be suppressed by controlling the ratio of halogen to alkane, yet this method is not much practical use use in the laboratories, since the boiling point of these haloalkane are quite close, hence cannot be easily separated. However, in industries, such complex mixture can be easily separated using long fractionating column. In this case of a higher alkane, the monohalogenation give a mixture of all possible isomeric halogens, indicating indicating thereby that all type of hydrogens, whether primary, secondary, tertiary, are substituted by the halogen atom. For example, propane react with the Cl2 in presence of sunlight. There is a formation of one chloropropane, two chloropropane. The relative amount of isomeric haloalkane, however, depend upon the nature of a halogen and the number of type of hydrogen primary, secondary, tertiary being substituted. In general, the age of substitution of various hydrogens follow the sequence tertiary, secondary, primary, but the relative rate vary with the nature of halogen. For example, with chlorine, the relative rate of substitution of tertiary, secondary, primary hydrogens at 298 Kelvin is 5 ratio 3.8 ratio 1, while with bromine it is 1600 ratio 82 ratio 1 at 400 Kelvin. Iodization is reversible, but it may be carried out in the presence of oxidization agents such as HiO3, HNO3, and HGO, which destroys the Hi as it formed, thus drive the reaction in forward direction. Example: methane plus I2, there is a formation of methane iodide and Hi. Fluorination of hydrocarbons with the pure F2 gas occur explosively. This is partly due to the low bond dissociation energy of F2 molecule and partly due to strongly exothermic nature of one of the termination step. This is so exothermic that the energy released is larger than that the required to break a single bond C bond, thereby resulting in the fission of the molecule. However, direct fluorination of hydrocarbon may be carried out successfully by diluting F2 with an inert gas such as N2 or argon. Alternatively, alkyl fluoride are most conveniently prepared indirectly by heating the suitable chloroalkane with the inorganic fluoride such as arsenic fluoride and some more. When the organic halide contain two or three halogen atom in the same carbon, see cobalt fluoride, or more easily available SbF3 is used. For example, by halide exchange, iodoalkane can easily prepared by from the corresponding chloralkane and bromoalkane by heating it within sodium iodide in the presence of acetane and methanol. This reaction is known as Finkelstein reaction and is based upon the fact NaBr being less soluble than NaI in acetylene and methanol get deposited during the course of the reaction. As a result, the equilibrium shift in the forward direction. Now we will discuss the fourth one from the silver salt of a fatty acid. Bromoalkane can easily prepared by the refluxing of silver salt of fatty acid with bromine in carbon tetrachloride. This reaction is known as Borodin-Hunziker reaction, or simply Hunziker reaction. Hunziker reaction is believed to occur by a free radical mechanism. The yield of the alkyl halide is primary, secondary, and tertiary. The chloroalkane can be also prepared by this method by using chlorine instead of bromine, but the yield are poor. With I2, silver salt give ester instead of iodalkane. Reaction is known as Birnbaum-Simonini reaction. Now we will discuss the physical property of alkyl halide. Physical state, color and odor. Alkyl halide are colorless when pure, but bromide, particularly iodide, develop a color when exposed to light. Methyl chloride, methyl bromide, ethyl chloride, and some chlorofluoromethanes and chlorofluoroethanes are gaseous at ambient temperature. Other chlorobromo-iode compounds are either liquid or solid. Many volatile halogen compounds are sweet smell. Melting and boiling point. The molecular mass of alkyl halide are higher than their parent haloalkanes. As a result, the melting point and the boiling point of haloalkanes are several degrees higher than those of the parent alkane, main due to their greater magnitude of van der Waals of attraction. For the same alkyl group, the boiling point of alkyl halide decrease in the order Ri, Rbr, Rcl, Rf. This is because there is an increase in size and mass of the halogen. The magnitude of van der Waals forces of attraction increases. Third one is for the same halogen, the boiling point increase with increase in the size of alkyl halide. Fourth one is the isomeric alkyl halide, the boiling point decrease with branching. This is due to the reason that with branching the surface area of alkyl halide decrease, and hence the magnitude of van der Waals forces of attraction decrease. Generally, the boiling point of chlorobromoiode compound increase as the number of halogen atom increase. Now we will discuss the solubility. Even though alkyl halide are polar molecules, they still are insoluble in water. This is due to the reason that they can neither form hydrogen bond with water, nor can they break the hydrogen bond already exist between water molecules. However, they are quite soluble in organic compound of low polarity such as petroleum, either benzene, ether, chloroform, carbon tetrachloride, etc. Since the intermolecular force in the halo compound are similar to those in the above solvent density, alkyl fluoride and chloride are generally lighter than water, whereas alkyl bromide and iodide are heavier. Their relative density follow the rule Ri, Rbr, Rcl. Among the alkyl halide, methyl iodide has the highest density. However, as the size of alkyl group increase, the density of the alkyl halide decrease. Now we will see the stability. Since the strength of CX bond decrease in the order CF, CCl, CBr, Ci, therefore the stability of alkyl halide having the same alkyl group decrease in the same order: alkyl fluoride, alkyl chloride, alkyl bromide, alkyl iodide. That is why alkyl iodide on standing become violet or brown because of the decomposition in the presence of light to give iodide. Further, because higher the stability and easily available, the most commonly used solvent in industry are organic chlorides rather than bromides and iodides. I hope you understand this lecture. One more point is left: inflammability. Organic halogen compounds are less inflammable than the corresponding hydrocarbons. The inflammability, however, decreases with increased halogen contact. Since organic halogen compounds are good solvent for fats and oils and also do not catch fire easily. Polychloro compounds such as tritetrachloroethylene are widely used as solvent for dry cleaning. Tetrachloride is used for fire extinguisher under the name pyridine. I hope you understand the lecture. Now we will discuss in another video. Thank you. Have a nice day.